Welcome to our video. In this video, I will talk about our research paper titled Tree-Based Mining of Fine-Grained Code Changes to Detect Unknown Change Patterns. First of all, I will talk about edit script. Edit script means a code difference between two versions of code. Here is two versions of code means code before change and code after change. And by using a tool that generate edit script, we can get edit script like this automatically. I think one of the popular edit script generation tool is Unix Diff. There are two operations in Unix Diff: insert and delete. And as you know, Unix Diff is line level granularity. Here is an example of Unix Diff. And prefix minus means this line was inserted, deleted, and the prefix plus means these lines are inserted. Now I talk about the change patterns. Change pattern means a frequent sequence of editing operations in the edit script. There are three edit scripts in this slide. The first edit script includes two editing operations: insert A, delete B. And the second edit script includes three operations: insert A, delete B, and insert C. And the last edit script includes also three editing operations: insert A, delete B, and insert D. And as you can see, these three edit scripts share two editing operations: insert A, delete B, so they can be called as a change pattern. And change patterns are useful. For example, developers' change patterns can be used to realize code completion. And also, bug fix change patterns can be used in the context of automated program repair. Like this, change patterns are used in a variety of applications in the software development and software maintenance. Our research is based on this paper. This paper is mining fine-grained code changes to detect unknown change patterns. This paper is an ICSI paper. And this paper proposed a new technique to detect change patterns. But we think there is a, to summarize the technique, first of all, the technique monitors input to the IDE and then calculate code difference at regular intervals automatically. And then the technique extract patterns of editing operations. We think their technique includes a couple of issues. The first issue is their technique can be available only in IDE because their technique monitors the input to the IDEs. And the second bigger issue is in the extraction. I mean, the extraction accuracy is not so high. I will talk about the second issues in detail. Here is an example of change A, and here is another example, change B. These two changes, as you can see, very similar, but are slightly different. These two changes, their technique extract change patterns. This change pattern includes insert if and insert return, because both of these changes include return statement and if statement. But please see this code. These change patterns ignores positional relationships between if statement and return statement. Because there is no information about where return statement was inserted in the code. We think this is a big problem. So, and this problem trigger their techniques to be inaccurate as a change pattern. So, in this research, our research purpose is accurately extracting change patterns from a Git repository. As I said in the previous slide, prior techniques extract change patterns from editing operations like this. And each operation is treated independently, and their positional relationships in the editing edited program element are not the edited program element treated independently. And on the other hand, in our technique extract change patterns from ASTs, means abstract syntax tree. So by using trees, our technique can consider the positional relationships between the manipulated program element. Here, this slide summarizes the proposed technique. The input to our technique is Git repository. And first of all, our technique identifies commit in the Git repository, and then calculate edit script from each commit. And edit script is generated. And from the edit script, our technique next build unified tree. I mean, unifying two trees of before and after a change. And the unified tree is constructed. And then our technique extract change patterns from the unified trees. Okay, let's talk about this part of our technique. This part, our technique utilizes gum trees. Gum tree is an existing technique that extract editing operations from two versions of code. There are 4 kinds of operations in gum trees: insert, delete, move, and update. Here is an example of gum trees editing operation identification. For example, this private token was identified as delete, and this parameter was identified as inserted, and this literal gum was identified as updated, and this statement was identified as moved. To realize this identification, gum tree internally build ASTs from the code before change and after change, and by comparing the 2 versions of ASTs, gum tree identify these editing operations. Okay, next I talk about this part. Unified tree. Unified tree means a tree into which AST before and after change are combined. It is not difficult to build a unified tree. Just the inserted node and the moved subtrees are added to AST before change. Here is an example. This is the AST after change, and this is the AST after. This is the AST before change, and this is the AST after change. And first of all, AST before change was copied here, and then the inserted node in the AST after change was added to here, and then the moved subtrees in the AST after change is also copied here. Copied here. So, and in this process, our unified tree is constructed. It is a very easy way. Next, I talk about here pattern extraction. To find the tree patterns, we utilize Flect, which is an algorithm to find frequent tree patterns from a labeled ordered tree. Here is an example of finding patterns that appears more than once. Here is the input, 2 trees, and output is identified frequent subtrees. And in this example, frequent subtrees appearing more than once is identified. But of course, we can configure the threshold. For example, detecting patterns more than twice or more than tens. And in this slide, there are 4 unified trees here. And by using Flect, we can identify these frequent subtrees in an efficient way. And these frequent subtrees means change patterns in our research. Like as I explained in this slide, our technique extract change patterns, tree-based change patterns. Oh, sorry. And we have implemented our technique as a software tool and published in the GitHub. So if you're interested in our research, please use this tool. Okay, now I talk about the evaluation. The question in the evaluation is, does the proposed technique accurately extract change patterns compared to existing techniques? Okay, we need to compare our technique to the prior technique, but unfortunately, prior technique does not publish the tool. So we need to implement it. We need to implement it, the prior technique as a tool by ourselves. And we did that based on the description of the XC paper. And here is a summary. We called the prior technique base. Base output a set of editing operations as a pattern. And the base gives priority to execution speed, and some oversight is allowed. And there are 3 kinds of operations in the base: insert, delete, update. Oh, sorry. There is no move operations because base is not a tree-based approach. And the input is Git repository, and the output is a change pattern. Here in change pattern means set of editing operations in the base. And now we compare the TC2P, our technique, with base, a prior technique. Here are the experimental configurations. We use about 200 Java project collected in the prior research as a target project. And target commits are latest 1,000 commit in the each target project. And we used 10 as a threshold, to be detected as change patterns. Here is a detection result. TC2P detected 62,000 change patterns from the 200 projects in total. And on the other hand, base identified about 500,000 change patterns in total, and they share only 10,000 change patterns. Now I focus on the change patterns detected only by TC2P. 62% of change patterns include move operations. And this is why these change patterns are detected only by TC2P, because move operation is not included in the base. And the remaining 38% are base failures. I mean, somehow base can't detect such change patterns, but we don't know the details of the reason. And from this result, we confirmed that the TC2P was able to extract change patterns with a richer information. Next, I focus on the change patterns detected only by base. They occupied actually 97% of change patterns that are identified by base. And we visually checked 30 random selected patterns. And 29 of the 30 patterns includes different changes. And different changes have been made in the single change pattern, and they shouldn't be detected as a pattern because they are different changes. They are actually different changes. And the remaining 1 change patterns is expressed with using move operation in TC2P. I mean, in the pattern of base, the change pattern includes insert operation and delete operation, but the same change pattern is expressed in the TC2P. It includes move operations. So from this result, we confirmed that many of the patterns that were not extracted by TC2P but were extracted by base were incorrect. Now I summarize my presentation. The prior technique has the issue of only available in IDE and inaccurate. So in our research, we proposed a new technique to extract tree-based change patterns. In our technique, gum tree and frequent tree pattern mining are utilized. And we compared TC2P, our technique, with base, the prior technique. And our technique was able to detect the change patterns without omissions and more accurately than the prior technique. Okay, that's all. Thank you very much.